very much for inviting me here. It's a pleasure to have a chance to talk about this work. STM is scanning tunneling microscope, so it studies now of single atoms sitting on some surface, and it's some kind of battle of the resonances. So you heard something about the Kondo resonance, and you know a lot about the Fano resonance. And so, of course, Mark has told you something about what happens in these systems, but I'll tell you more about what happens when these two resonances duel. So, of course, what you've done is you've invited the theorist. The really hard work was done by Mike Cromie and his associates at Berkeley. And in fact, a good part of my talk will be devoted to showing you their beautiful results of scanning tunneling microscopy. So I will begin with an introduction to the Kondo effect. I realize that Mark Kastner has just told you a lot about the Kondo effect, but I figure the more times you hear it, the more likely you are to believe it. So after saying some of the same words and maybe some of my own, I'll then go on to describe the actual measurements that were done by Cromie and his group, doing scanning tunneling microscopy imaging of single magnetic impurities. And if you haven't seen this, this is really, really something to behold. So what they found in doing this is not only could they see images in real space and see atoms, but of course they could do spectroscopy as well and look at the densities of states, or so they originally expected, of the impurities. And they were expecting to see the Kondo resonance in the density of states. And of course what they saw, and probably some people in this audience could have predicted that, is that they saw Fano resonances instead. And so this led to the question, which is how I got involved, is why is there a Fano line shape for this Kondo resonance when you know that this Kondo resonance is purely a result of strong interactions? That is, if there are no interactions in their system, there's no Kondo resonance at all. And so I hope that what I can tell you this afternoon will let you understand why you actually get a Fano line shape even for this seemingly purely many-body effect. And I'll say a little bit then about what you can do once you understand this Fano resonance in terms of interpreting which term is dominating the process of electrons leaving the scanning tunneling microscope and eventually making it into the gold substrate. And you'll find that what we found in the end is that it's really this indirect coupling that we're being dominated by. Instead of electrons going directly onto the magnetic impurity, they go through the host and scatter off the impurity. At least that's our interpretation, and I'll show you exactly the evidence that has led us to that. And at the end, I'll summarize. So just to show it to you again, schematically, of where Kondo scattering was first observed. So here was some piece of metal, which I think was copper with magnetic impurities, which were iron. And what was observed was that, of course, as you lower the temperature, the expected thing happens, and the resistance drops because you're not scattering off phonons as much. But instead of the resistance continuing to drop in this system, it started to increase again. And these measurements were done in the 30s. And this minimum of resistance was the first observation of the Kondo effect, because this growth of the resistance, which was logarithmic and then saturating, reflected some special property of scattering off of magnetic impurities, which is not there if these impurities are not magnetic. So ordinary non-magnetic impurities don't give you this increase of resistance. And the first person who wrote down a correct theory of this was Kondo, and of course that's why it's called the Kondo effect. And he pointed out that this process where an electron that's coming in with, say, its spin down, and an impurity has its spin up, and the electron leaves the impurity having exchanged spin, gives you a very different behavior than just electrons scattering elastically off of some impurity without spin. And he was able to show this just by going in perturbation theory beyond the leading order. So everyone had written down the leading order scattering. There was no difference between magnetic and non-magnetic. So Kondo had the Sitzfleisch to go to the next order and show that, lo and behold, everything was different, and there was this logarithmically diverging, or as the temperature was lowered, logarithmically diverging scattering. And of course, what Marx referred to is, how do you get this logarithm to stop? And that required, another 20 years of theoretical activity before this was understood. Now, again, this understanding of how to treat and think about magnetic impurities owes a lot to Anderson. And so he wrote down the Hamiltonian that lets us understand where the magnetic impurities are coming from, and this was then essential in the theoretical developments for the Kondo effect. And so here's just another picture of the same idea, that you have some localized state, which could be one of Mark Kastner's artificial atoms, or in this case it could be a single atom, say a cobalt atom, and there's some orbital here, or possibly more than one orbital, which in the absence of any Coulomb interaction would just have some spin degeneracy. So there would be a spin up version of the orbital and a spin down. However, there is, of course, a Coulomb interaction. This is a very tightly localized state. And so if you put one electron onto this orbital, say the electron with spin up, it's going to cost some large additional energy U to put on an electron with spin down. The Kondo effect occurs in this regime where you've attuned the Fermi energy to lie between the energy to add this first electron and the energy to add the second. And of course, this is exactly the situation where you get a magnetic impurity, because the idea is that energetically you certainly want to put one electron on there, but you can't put two. So being stuck with one electron means you're stuck with something that now can either be spin up or spin down, or some fluctuating combination of them. The picture then, if you look at the local densities of states of this localized orbitals, are of course that you see some resonance sitting down here at the energy epsilon d, and if an electron is there, there's some resonance here in the other spin channel at epsilon d plus u. But in addition to that, there's this miraculous additional resonance sitting right at the Fermi level. And of course, the point is, you move the Fermi level up and down, this resonance tracks it. It's purely an interaction effect. There's nothing in this original model that singles out the Fermi energy. It's purely this interaction effect due to coupling of this interacting system to a continuum. And just to sort of give you an idea of why you have this resonance, there's something called the Friedel sum rule, which tells you that the transport at the Fermi surface, the phase shift for scattering at the Fermi surface, depends on the occupation of this state. And the idea is that if you have only one electron here divided between spin up and spin down, your occupation is 1/2. And an occupation of 1/2 guarantees you a phase shift of pi over 2, which means there has to be, at zero temperature, a perfect transmission through this object right at the Fermi energy. So you can understand the necessity for this peak in terms of the Friedel sum rule. Now, what people were able to do for a long time was to look at this Kondo effect by various techniques that looked at multiple atoms at the same time. So either photoemission or some kind of tunneling experiments. And I'll show you just briefly what those look like.
What happens if the Fermi energy corresponds to one of the levels?
Yeah, if the Fermi energy corresponds to one of the levels, then the situation is initially much less interesting. If you scan the Fermi energy up here, you actually see in the transport, for example, if you're looking at conductance through here, you would just scan out this bare resonance, just as if you were non-interacting. But what would happen at low temperature is you would come up this side, but then you'd be in this Kondo regime, where the Friedel sum rule guarantees you perfect transmission. So at really zero temperature, if you were thinking about this as transmission or conductance, your conductance would get stuck up here at perfect conductance until you finally put the second electron in, and then it would come down again. In a sense, if you turn this on its side, this was what Mark Kastner was showing you, that for the weakly coupled system where your temperature is much higher than your Kondo temperature, you just see these two peaks. But as you go to this strongly coupled regime, this valley in the middle fills in, and eventually everyone believes that at zero temperature you just see absolutely perfect conductance over the whole range of gate voltages. So just to flash this up, people will look at photo emission, looking at the energy-dependent emission of electrons excited by light, and this Kondo peak appears at the Fermi surface as you lower the temperature. And it's true, it's not just thermal smearing, but the Kondo peak actually only develops as the temperature drops below the actual Kondo temperature. And similarly, here's a situation where people were looking at transport, but again, there was a whole ensemble of magnetic impurities, and they were looking at some Kondo peak associated with the average over all of those. So the new development that has brought this question back to life is the ability to look at now single atoms. And so this is where scanning tunneling microscopy comes in. It's a tool that can be used both for imaging and for spectroscopy, and of course for combinations of the two. In the usual imaging mode, one has a tip here, which one has control over its height and its lateral position on the surface. One has a surface of interest. There's a voltage that one can apply, and one can measure currents from the tip to the surface. And in the simplest case, you would imagine that you're just looking at the linear response conductance. So the bias between the tip and the surface is some very small amount, and you're measuring some current between them. And in some mode where you kept that current fixed, you could then scan across the surface and decide how high you had to move the tip in order to get the same wave function coupling from the tip to the surface. And that would allow you to pick out various bumps and wiggles in the surface. And the amazing thing is that under many cases, at least using the right tips and the right surfaces, this is good enough to give you atomic resolution. In addition to this imaging mode, you can also use this for spectroscopy. So here the idea is now to apply a finite voltage, not infinitesimal, but some finite voltage, and to look at how the current from the tip to the surface changes as you increase the bias between the tip and the surface. And that change in the current, d voltage, will tell you about the coupling of the tip into this new band of states right at the voltage of the tip. And so by looking at the differential conductance, you're looking now at the local density of states in a position and also at some energy, EV, above the Fermi energy. So you can do both imaging and spectroscopy. Now this is one case where knowing how something works and seeing it are really different. And I think in this case, seeing it is much better than knowing how it works. So here's a picture that comes from Mike Cromie and his group of imaging cobalt atoms on a gold 111 surface. And here is some piece of the surface, 400 angstroms by 400 angstroms. And these are individual cobalt atoms. You take the gold surface, you look at it, they're not there, you deposit some fraction of a monolayer covering, and there are these individual cobalt atoms. Now, in addition to it's looking at individual atoms, you can see some other things. There are some features here that seem to have nothing to do with the cobalt, that are just these striped patterns in the gold. This has to do with a surface reconstruction of a clean gold 111 surface called a herringbone reconstruction, where the atoms on the surface all move around a little to lower their energy in a characteristic way. And you can see other nice things too. You can see some of these sort of wave-like ripples on the surface that actually seem to track the positions of the cobalt atoms. So you see now that there's some interference phenomena due to scattering of the surface electrons off of the cobalt, just as you might scatter waves off of a bunch of rocks out in the ocean. So I think this is a pretty incredible thing. What's where? This?
There's sort of a hole in the upper left-hand quadrant. Yeah, there.
This just may be an interference minimum, that there are a bunch of waves that come together, and there's just some moment where there's a dip in the, a destructive interference of various waves at the particular energy. I should say this is all done at one particular bias voltage. So as you did a spectroscopy sweep and took another snapshot of this, this minimum might become a maximum. But this is at that energy. There's some destructive interference of the surface waves at that point due to it scattering off some set of surrounding cobalt atoms.
The wavelength seems fairly constant. Is that the Fermi wave vector?
Yeah, this is basically the Fermi wave vector, absolutely, of this particular band in the gold. There's a two-dimensional surface band in the gold, and that's what's dominating all of the features here. But of course, you can do this spectroscopy mode, and I think you already saw this data. And this is what Cromie and company were all gearing up to do, was to do spectroscopy and see this beautiful Kondo peak coming up out of the background. So if you're sitting off of the cobalt atom, there's nothing particular happening at the Fermi energy. And then when you sit right on top of a cobalt atom, there's your Kondo peak. Oops, it's not a peak. It's a dip, some asymmetric line shape. And of course, everyone knows something about the Fano line shape, even if they don't understand it. So Cromie and company were able to realize that they were certainly looking at something that looked like a Fano line shape. But it wasn't at all clear why this Kondo system was giving a Fano resonance. And of course, it's sitting where they expected it. So it certainly looks like it's due to this Fermi surface Kondo resonance that they were anticipating. But it didn't have the simple Lorentzian form. So one reasonable question at this point is to say, well, maybe you're kidding yourself. This is some accident of cobalt on gold. And the answer is it's not the only Kondo system that shows it. It's merely the best. So there's widespread Kondo behaviors on using either gold substrate or a silver substrate. And of course, cobalt's a really nice one. You see a beautiful shape. But nickel has also got something going on, maybe a little bit more complicated. Some of these transition metals don't look so good, but there's titanium is, again, something very clearly happening right at the Fermi energy. And it doesn't matter whether you're sitting on gold. You can sit on silver. Again, cobalt looks pretty nice. Titanium looks nice. And there seems to be something going on in iron, and again, something going on in nickel. So I don't think there's any question that this is just an accident of something special happening with cobalt. It's a general property of magnetic impurities.
Question.
Yeah.
Is it clear it has to be a magnetic impurity? Have people looked with anything else?
Yes. So I haven't shown the data, but they have non-magnetic impurities. I think it was sulfur that they were sitting there. And you see it. You do the imaging. It's perfectly clear. You can see individual sulfur atoms. Nothing happening at the Fermi energy. So another thing that's worth looking at is how does this depend on the interaction of the tip with the surface, not just having to do with tunneling and measuring the density of states, but with the electric field effects. And this is something that Bill Gadzik has done some very nice work on. In this case, they were actually far enough away. The tip was far enough away from the atom that the electric fields due to the tip don't seem to be having any effect. And the way to see that is just to back the tip farther and farther away. And indeed, they were able to see that while the resistance is going up by orders of magnitude, the line shape isn't really changing. So the physics that goes behind this line shape is not due to the electric fields due to the tip. It's something intrinsic to the cobalt atom on the gold, and the tip is now just probing the electronic structure. Another natural thing to do, though, is to start moving the tip not far away from the cobalt, but off-center, but not very much off-center. And there you see some very clear dependence that this rather pronounced asymmetric line shape gives way to a more symmetric dip at 4 angstroms and finally toward basically a background of no clear signal at 12 angstroms. So there is some evolution of the Fano parameter with lateral displacement from the cobalt. And you can see that very clearly in this scan here, where they've moved from one side of a cobalt atom to the other. No resonance. The resonance develops. There's a nice clear asymmetric resonance, and it fades, and as it fades, it becomes more symmetric. And this has been studied down in the bottom in more detail of cobalt and copper by Noor et al. But here are the data on the top from Cromie. And the only point I want to make here is that this really looks like a Fano resonance. That you don't. Well, I have a little trouble lining this up, but they had no trouble fitting any of their data with a Fano resonance as long as they were able to use this Q now as a parameter. And the Kondo temperature was inferred from this width. So it does look like they're getting the right energy, a reasonable energy scale for the Kondo effect. But indeed, it's a Fano resonance. It's not a simple peak in the density of states that we were expecting for Kondo. And so the rest of the time, I'm going to try to explain why, when you have this, even though you have this many-body resonance from the Kondo effect, you get a simple Fano line shape, which was, of course, originally derived for some problem where there's a state hybridized with a continuum, but none of this fancy many-body resonance, just an ordinary level hybridized with the continuum. So just to say it again, the puzzle is the Kondo resonance is entirely due to interactions among electrons, not there without the interactions. We know all about Fano line shapes, but this is when some level with no Coulomb interactions is hybridized to a continuum. So why are we getting Fano line shapes for Kondo resonances?
Well, the hybridization of a discrete level to a continuum has to come about due to interactions, right? Yeah.
Okay, I wanted hybridization in my language is not an interaction. Interaction is something that involves an electron-electron interaction. So not one electron making a transition from a localized state to a continuum state or between two continuum states, but something that really involves two discrete electrons interacting with each other.
Well, that's like the line shape in helium, where there are only two electrons. I mean, the classic Fano line shape does derive.
Well, the question is, I mean, okay, there are interactions everywhere. Of course, all electrons interact. But when you run the models that all of this that Fano worked with would be non-interacting in this language. Here is the. So this is what I mean, and Hamiltonian is better than words here. So this is of course the non-interacting resonant level model. We saw this in the copy of Jerry Mahan's book, and this is something where you of course have a discrete level here, a continuum of states. I've given it as some summation, but you could give it as some integral over states, and some hybridization that mixes the discrete level with the continuum. What there is not here is a term that involves products of four electron operators. So something that looks like d dagger d for spin up with d dagger d for spin down. So as long as you can write it here, even though maybe the level itself is something that depends on Coulomb interactions, and even though maybe the hybridization depends on Coulomb interactions, if you can extract out a Hamiltonian that looks like that and doesn't have any additional terms, that for me is the non-interacting case. And when you need explicitly to include a term that has d dagger d, that's going to be the interacting case. And what I'm going to show you is that even when you include this d dagger d term, you can end up with the same Fano line shape for your many-body resonance. So here, you can't invite a theorist without expecting green functions, but They'll keep it as very, very simple level. So of course you have this Hamiltonian. This is the green function for the resonant level. It's just a resonant denominator with some self-energy, and the self-energy is due to the hybridization of this level to the continuum. And so, of course, what you get if you look at something physical like the density of states for this resonant level, which is what you'd measure in a transport experiment or in a photoemission experiment, is you get a nice simple Lorentzian resonance, at least as long as there's not much energy dependence of this self-energy. The width is going to be given by the imaginary part, and the center of the resonance is just the bare level energy plus some real part of the self-energy, which is a Hilbert transform of the imaginary part. So that's the non-interacting resonant level model. And of course, if you now take the Fano approach, you can get Fano line shapes for that model. And so what I'll first do is just show you these results and then point out that it's all the same in the case where you have implicitly an interaction Hamiltonian that gives you a Kondo effect. So the case we're interested in is we have some STM with an atom and a surface. The resonant level model is just describing the atom and the surface. There's your discrete state, and there's your continuum. And what we're going to add to that now is processes where an electron comes from the tip and either goes directly into the continuum, or it can go from the tip to the atom. And of course, the atom is already hybridized with the continuum. So we have these two different ways of getting from the tip into the surface, two different ways of eventually carrying current. And of course, they're going to interfere. But there's the term in the Hamiltonian. You can go straight to the atom from the tip, or you can go to the surface from the tip. When you calculate the current then, how much current flows from the tip eventually into the surface here, just to the lowest possible order, the lowest order in this tunneling Hamiltonian from the tip. So just to order m squared, you get the following result for this differential conductance, which is, of course, something that the experimentalists can measure. It's got units of conductance. That's good. The density of states of the tip we're not going to be interested in. We'll think of this as being constant. And then it's the imaginary part of something describing the coupling directly to the continuum. So this is just measuring the density of states of the surface. And then this term, which is where all the interest is, and this says, well, there's one term that just tells you about the density of states of this discrete level coupled to the surface. And then there's a question of the various pathways I can take from the tip to the surface, where A has a piece that's a direct tunneling term and some kind of indirect term where I can tunnel into the tip, into the surface, and then scatter off the atom. And B is just this indirect process with no direct coupling from the tip to the atom. And of course, what you want to do for this session certainly is write this in the beautiful form derived by Fano. And so just a little bit of algebra takes you from there to here. And what you see is now that we've been able to rewrite this in the terms of the Fano line shape, where the Fano parameter is just this A term over the B term, and we have some energy here, which is just a rescaled energy. We're measuring as a function of voltage, so the thing that's changing here is the voltage, and it's just the voltage away from the effective position of this level made dimensionless by the imaginary part of the self-energy. And so, of course, this is all a treatment of this non-interacting resonant level model. And so, of course, we're going to get the Fano line shape. So that wasn't a big surprise. The surprise is that we don't have to do any more work to do the interacting case. So here it is. This is the key point. And I've labeled it key point to make that clear. Is that this derivation where we had this Hamiltonian for the resonant level, and we added the coupling from the tip directly to the atom and directly to the surface, this derivation never made any assumptions about whether there were or were not interactions on this atom. If you put interactions on the atom, if you put a term that looks like a Coulomb interaction between spin up and spin down, that's just going to give you some new value for the green function, or equivalently the self-energy of this atom coupled to the continuum. It's going to give you some new term here, but the rest of it is completely unchanged. So then we're free to go to a textbook and look up what is the green function or the self-energy for a Kondo impurity. And lo and behold, near the Fermi surface, the result is that the imaginary part of this self-energy of this interacting Kondo resonance is exactly the self-energy we'd had for the non-interacting case. It's just some constant gamma, and I should have written that this is just the same as the imaginary part of sigma 0, so nothing's changed here. The only change is that now the real part of the self-energy, instead of being some boring shift, has got some strong energy dependence. This term here actually cancels the usual part of the denominator. Yeah, we're good. So that first term in the real part of the self-energy actually is going to cancel this term here. So that's gone, and all we're left with is this linear term, which is saying that as you go through the Fermi energy, the real part of the self-energy is changing linearly with the energy itself. And the only thing that's happened, remember that was happening before in the original case. We just had the real part of the self-energy with some linear dispersion. But now we've got an enhancement factor of that, which is given by this gamma over some new energy scale, which is the Kondo temperature. And so the idea is that where we used to have a resonance which was with gamma, now, because the real part of the self-energy is moving faster, our whole resonance, our whole shift through the resonance, happens in a much smaller energy scale. It now happens in an energy scale given by the Kondo temperature. So all this Kondo many-body physics has gone into giving us a new resonance with a much narrower energy, with this new many-body effect giving us something called TK, but otherwise it just looks like a plain old resonance with a new width. So there you go. So the result is just like the non-interacting case. All the formulas are exactly the same. We still get a Fano line shape, only now the energy scale is not this broad scale associated with the hybridization of the bare level. It's this new many-body scale given by the Kondo effect. So now we understand where it's coming from. One can ask, hope for more to get something out of this. So what about this variation in line shape that we saw as we moved the tip? Well, we saw there was no variation with tip height. And so we might have expected, if we were tunneling directly into the tip and that was dominating, we might have expected that if we were tunneling directly into the atom, that would be very dependent on the tip height, because that will be a very localized state. We didn't see any variation with tip height. Moreover, there's another experiment, not done by Cromie, but done by Harry Manoharan on a Kondo corral, where he looks at now Kondo impurities here in an ellipse and looks at tunneling into the other focus. And he sees a very clear Kondo signature in dI/dV where there's no Kondo impurity. But what you can expect is that if I tunnel into this focus, there are all these indirect processes where I scatter off the ellipse, scatter onto this real Kondo impurity and back, and all of these have, of course, the same length. That's the point of an ellipse. So all of these are constructive. So what it looks like from both the tip height evidence and from this quantum corral is that one is being dominated by the indirect term. We're not talking about tunneling directly into the atom. So this term in in the numerator of Q looks to be small, we seem to be dominated by this indirect term where we tunnel into the surface and scatter off the atom. So there's been an interesting attempt now to actually derive Q from first principles by looking at this formula and calculating it for the real surface electronic structure of gold. And I think this is an interesting direction now to really make use of these Fano line shapes as a probe of surface electronic structure. So to summarize, the Kondo effect is observed in scanning tunneling microscopy of single magnetic impurities on a number of different magnetic impurities on a number of different substrates. It's a very ubiquitous phenomenon. The line shapes, at least in the cases that are now well understood, have a clear Fano form, and now we can understand that since we've seen that the Fano theory also applies to resonances of purely many-body origin. And the hope is that one can now move forward and use these line shapes in the Fano Q parameter to understand more about the electronic structure of the surfaces. And that's all I had to say.